Okay, so I was saying that it is a fallacy to say Tor is weak, but mixed systems are perfect. In fact, all anonymity systems leak, even perfect ones. The question is, at what rate do they leak? And we need to understand that before actually making rash judgments that we should shift to one technology or another. Now, the leakage that I have shown you so far is really under passive attacks. But things get worse when we actually start having active attacks, even the simplest active attacks, namely the adversary being able to use the service, or the adversary being able to just delay messages and inject messages into the service. Okay? So these are known as n-1 attacks or Sybil attacks. And here is the example of the n-1 attack that really illustrates that they can be very powerful if left unchecked. Imagine I have an anonymity system here. Let's imagine this is a single mix as part of a large network of mixes. What the adversary may do is they may wait for Alice, the target, to send a message into the anonymity system, and then they just somehow block all other senders for a while, or race them, if you want, and send many messages that are from the adversary. Now, at some point, the anonymity system, if it is a threshold type anonymity system and it waits for k messages, will trigger, and one message will come out to the friend of Alice, who the adversary wants to trace, and the other ones will actually go to a destination that is predetermined and known to the adversary, and therefore the adversary, just looking at the inputs and the outputs, will be able to trivially work out where Alice is talking to whom Alice is talking to. Okay, so that is the n-1. That's the n-1 bad messages. The final one is actually the target. Now, another, of course, attack, which is just the, kind of like trying to leverage this, ability of the adversary to create connections or inject nodes into the system, is if the adversary just pretends to be multiple users or pretends to be multiple nodes offering mixing services and just basically becomes part of the infrastructure, observes everything they have injected and they know, remove it effectively from any uncertainty they may have, and see what remains in the network in order to actually do the traffic analysis attacks we described so far. The solution to these attacks are delicate and have to actually be user accepted very carefully, right? One option is to authenticate users to ensure they are real and genuine. I mean, this to some extent avoids some forms of the n-1 attack. One could say, well, here, if somehow everybody had to show their passport before using this mixed system, and you could actually have some authority that you trust that they're all distinct people and good people or whatever, the n-1 attack would be harder. However, you can imagine that there exists no such authority that will for sure tell you that all of these people are different and distinct. We don't have public key infrastructures that do that. And there is a fundamental unease about, as a first step for accessing an anonymity network, asking people for very strong identification, right? I mean, you can imagine that, you go to an anonymity system because you want some privacy, and then it asks you for the stronger form of identification before you even can start participating. You start becoming a little bit suspicious about what exactly this system is about rather than anonymity. Another mechanism that we will see in a bit as well to avoid some forms of the n-1 attack is to do active measurements to detect if you're being blocked here and take countermeasures in the form of covert traffic. You can drop messages if they are delayed too much, and you can actually do some Sybil detection techniques based on social network or other things to avoid the Sybil attacks. All of those things are super experimental. None of them basically I can say, oh yeah, we've been doing this for 20 years, it's a solved problem. No one really knows what really to do about these things in real systems. Finally, and that will conclude the kind of pessimistic tour of mixing, there are what I call, and Paul Syverson worked on me with that, epistemic attacks. Mixed systems and onion routing systems, these attacks apply equally across, are complex, large distributed systems. Okay? In theory, to scale, they have thousands of relays, etc. Now, those relays need to be known to the users that have to somehow pick paths through them, know their public keys, know their addresses, know their status, and be able to route through them. Okay? Now, this is an enormous amount of information for users to have up to date, for keeping up to date about who's up, who's down, etc. Okay? Each of them has, as I said, a public key, etc. Even if you update it every half an hour, it's a few megabytes that you have to basically download to just have the latest state of the network. So, some clever souls have suggested in the past, well, why would you have all of it? In a mixed network or in an onion routing network, you only need to know the addresses of a handful of nodes to open a path and then end up to your destination, right? So why should you download all information about 7,000 relays or I don't know how many mixes to achieve that? And the answer to that is that if you don't, there are attacks that are possible that wouldn't be possible before. So imagine, instead of actually knowing all 7,000 relays in Tor, you know 100. However, which 100 you know is somewhat observable to the adversary. So the adversary knows you're the guy that knows those 100 nodes or those 50 nodes. Okay? So what does that mean? Now, the adversary observes a path opening because they happen to have compromised the middle node, let's say, in a path. So they're the middle node, there is a guard to their left, an exit node to their right, and taking Tor as an example. Now, first of all, they know that you're one of the people who could be using them because they, as a relay, are in your set. Okay, so that already reduces the anonymity set of all the people who could actually be relaying communications through them to just those that know about them. But then what else do they see? They see a connection opening from a guard relay. Well, that further reduces the set of possible people to those that know both the corrupt node and that guard relay. And then from that middle node that is corrupt, the connection continues from the guard relay to the middle node to an exit node. So that again further reduces the possible initiators of the communication to those that have known those three nodes. Okay? And therefore you radically decrease the potential anonymity set size of the people who could have initiated that connection to only those who knew those 3 out of 50 out of 7,000 relays, which actually turns out to be statistically a small number at the end. Okay, so what?
But is there a real reason why to give different?
Yes, there is a reason why to give different relays. Absolutely. If you don't give different relays, so for example, to run with your suggestion, you say I have 7,000 relays, but I always give tranches of 100 to different people. Okay? Then what happens in effect, you're splitting your network into many different subnetworks because people don't relay traffic so easily across them. So you can do more sophisticated things. So for example, giving overlapping things and things like that, but that inevitably reduces the anonymity. The question is a question of degree, okay? Rather than a question of whether. You're always worse off than knowing them all. And there are some ways that will make you less worse off and some ways that will make you more worse off. So you have to measure. There is no solution. Now, one solution, though, is to say, well, I will let my clients learn a subset of the routing information. However, I will not leak to the adversary which subset or which subset of the nodes they know about. This is a variant of PIR, private information retrieval, and we will revisit that topic. In effect, what Tor does today is the trivial version of PIR, which is download the whole database. And we know that this is a trivial PIR solution. You could actually use a less trivial solution, but as we will see, as they stand, PR solutions are too expensive computationally or resource-wise to be able to do that at the scale that Tor does. Okay, and in fact we have worked on that to solve that problem. Okay, any questions so far on the very pessimistic tour that I gave you of mixed networks to illustrate that mixed networks, it's not just that they were not chosen and not adopted out of some kind of weird spite or whatever. It's actually that they have fundamental problems. It's not that they are a solved problem. Any question? Yes, please.
Just maybe say it, but fast for me. The So the corrupted relay, it means that we assume that an adversary may somehow capture a relay and know all the...
Or they are their relay and they have put it in the network. Huh?
Every user is...
No. What I mean is that the adversary may say, oh, I would like to offer a Tor relay. You can just pin your computer now and become a Tor relay. And if you're evil, you can, you can start doing traffic analysis right now. Now, of course, Tor security relies on the fact that you do not control enough computers, etc., to compete with the 7,000 relays. So your capacity will be reduced in order to observe a big subset of the network. But if you do a back of the envelope calculation, you wouldn't actually need many millions in order to start competing with that kind of bandwidth. I mean, 300 gigabit a second sounds like a lot, but a few million will get you a long way towards that. Yeah? That's what I mean by a corrupt relay. It doesn't have to be some relay that was good and got hacked. It could just have been a bad, yeah, whatever. Yeah, exactly. No one tells me that they haven't, right? Okay, cool. So, mixing has problems. Tor has weaknesses against a global adversary and claims security against a partial adversary. The problem is, though, that it doesn't even achieve that. Okay? And this is really sad for a security system. I mean, if a security system tells you, I am weak against that adversary, it is a bit unfair to try to claim that it is insecure against another adversary. But if a security system tells you, I am secure against that small class of adversaries, and then even within that class it shows weaknesses, that is a fundamental problem. And let's actually start looking at how do we do traffic analysis of Tor to even basically find weaknesses within its threat model. Okay, so let's actually first look at the unfair attack. We'll be unfair for a second. We will say, okay, let's imagine that I have an onion routing network, and let's imagine that I have a global passive adversary. How would I go about tracing streams in Tor? Right? I see a stream coming into the network, I see a stream coming out of the network. Are they the same stream or not? So this is basically what our paper from 2004 did. Just to illustrate that, no, Tor is definitely broken against global passive adversaries. Don't even claim basically that this is not the case. So what we did is we took basically a model of a stream of packets going into the Tor network. These are cells over time of traffic. And then what we did is we modeled either the whole Tor network or a particular Tor router simply as an exponential delay router, right? I mean, it's an infinity queue, particularly if this is Poisson, but basically each packet gets received, it gets delayed for systems reason, not for security reason, using something that we model as an exponential delay. And many of those streams potentially get multiplexed together. Because people said, well, actually you get security not because of the delay or the mixing, but because of the aggregation effect. It's really the aggregation that surely must be buying you a lot. And that speaks also to the issue of cover traffic, that is mixed together. So what we have now is two output channels. One of them is basically a mixture of the input signal and other signals, and the other one is just the other signals. Okay? And the question is, this input signal here, this input stream that came into my router, which output link is it in? And this is not trivial. I'm not presenting some kind of Mickey Mouse example. It's, if you look at it, it's generally actually quite difficult to tell. Both of them are quite busy. It's not a trivial problem. So what do? We basically take this delay function and we convolve it with the input signal here. And that creates a template, as we call it, that basically is it's a highly simplified model of where we expect the mass of traffic to be on the output link that will match that input signal. We also model the fact that some added noise was put into this output channel, like the other streams basically that was multiplexed for. And then we basically calculate the naive probability, point-wise, without actually taking into account the joint probability, that signal was actually generated by sampling this pattern, or that signal was used by sampling this pattern. Okay? And lo and behold, when we actually calculate the likelihood ratio of those two probabilities effectively, we end up for a while being uncertain, and eventually, of course, we end up having one side of the likelihood overtaking the other. And interestingly, particularly when significant events happen, like one stream overtakes the other, or there are a few cells with each other, etc. There are discontinuities you don't learn smoothly usually, but that is how it is. Eventually, estimation theory and decision theory tells us there will be a point at which we will be able to tell with perfect accuracy, or arbitrary accuracy, I should rather say, whether it is the top stream or the bottom stream that carries the input signal. Okay? That's how you do the analysis if you cheat effectively against Tor and you say, well, we'll attack Tor with a global passive adversary instead of this partial adversary. Any questions here? That was contentious back at the time. Nowadays, everybody's like, yeah, if you see the two sides of the connection, game's over. Fine.
How feasible is this global passive adversary?
Well, that is a very good question. So, the second argument then was, following all of this, back in 2004, adversaries, they cannot really be global. You guys are just like paranoid whatever, right?
This is not really global. This is just the input and the output.
Yes.
It's not really global.
It's not really global, but the idea is that if I have a lot of relays and all that stuff, exactly.
No, but it's just a question of who is controlling the access network of the
True.
two ends.
True. So that's actually a very interesting point, right? Because to some extent, this is visible by the server, this is visible by your ISP. If they work together, that's all you need. You don't actually need to see all the links. That's a very good point, right?
Was there a work which analyzed in the case of real global adversary? Because that's, of course, additional information.
No, there isn't. Okay, so people then said it is, okay, so let me rephrase that. People said, what is the probability that an adversary controls the input and the output, right? And they said, well, assuming that they can independently control with some probability the input and the output, probability C, it's about C squared, right? And this is actually why in Tor, increasing the path length doesn't really make a difference, right? The path length is not a security parameter because the probability you observe the first node, let's say, and the probability you observe the second node, is all that it takes to actually break the system, no matter how many nodes there are in the middle, okay? So they said, well, that's the security of it, okay? That's as far as it went. And then people said, well, how easy it is to instantiate that? Well, C squared, that's it. And then we started doing attacks, yes?
So, but then we still went for 3 and not 2 nodes.
Yes, so it's interesting actually. The third node, according to my conversations with Roger, and I don't want to misrepresent it here, maybe it's my memory playing tricks, is really to mitigate coercion attacks. So if you are a corrupt node, and you happen to be one of the two, let's say, right? Then what happens is, if you have a path of 2, you can see who the other node is, and you can go immediately and get them, okay? Whereas if there is one in the middle, you'd have to go, presumably that takes some time, by then the connection is dead, the ephemeral keys are all gone, and then you discover who the third one is. At that point, it's too late to actually go and do an online attack if you want to grab those keys, okay? And this is why they introduced that middle node in the middle, to avoid the kind of coercion or takeover attacks that could be done online, and basically create enough of a window of time for the 10-minute rotation to kick in, and by the time you basically can legally, for example, coerce the other 2 nodes in the path, it's too late. Yeah? Because you cannot do the attack on parallel. You have to do it sequentially. You have to go to the one node and then to the other. Okay. Yeah.
You said it takes some time to decide.
Yes.
And does it? How does it vary with more signals getting in, getting out? Does it? Is that a function? Is the decision time?
Absolutely. So there are 2 things that matter in this analysis, and they influence effectively how quickly you make the decision in the following way. The longer the delay, the slower you will be able to make that decision, and the lower the volume here, okay, the quicker you will be able to make that decision as well if the volume is regular. If the volume is irregular, so here we have assumed Poisson inputs, okay? But if basically now you assume different types of inputs, that insight goes out the window, right? But if you assume super regular inputs, basically, is it the lower or the higher? That's a good question, actually. Yeah.
Well, is a good assumption for like trying to analyze how protected people who are using Tor even to assume Poisson in the input element?
No, Poisson distribution of the input makes gives an advantage to the defender, right? So it actually is good for estimating how good the attack is rather than how good the defense is.
Okay.
Right, it's the other way around. So if you actually want to make an estimation on the defense, you would have to assume the worst shape of traffic.
What I'm really trying to ask is if you take a real life, if you try to test it in real life, you will set up your two nodes and you can plug two nodes and maybe you will take a chance that, or maybe you can simulate a small code networking or a private network. Would you still be able to decide in the time that you need to decide before we change the keys, they change the time? Actually physically realizable in...
Yeah.
Okay.
The answer is absolutely. You would be able to decide it like within a few cells, and a normal web session is like hundreds of cells. The reason for that is, and we will come back to that maybe in a second, that web traffic, and like Poisson traffic, is extremely bursty and extremely heterogeneous, right? So it is not like two Poisson, processes that, are like that. In practice, web traffic is silence followed by peaks that are themselves of very varying heights. And because Tor does not actually change that into any kind of inter-regular traffic, make different streams regular, like within basically a couple of requests, it is unlikely that anyone else in the world made requests exactly at those times, let alone that the traffic that came back had that shape and that timing.
What if I would force all my clients to send a regular?
Well, then we will see what happens in a few slides, because that's a potential, but we will see that this is not trivial. Yes?
I want to ask you, this assumes input and output observation, but if I basically can watch like the first router, watch
We will
traffic
get to
going
that.
in, I think you can disambiguate where the client's traffic is going anywhere, right?
Yeah, we will get to that in a second. Okay, cool. But first, before we go there, let me actually say a cautious thing. So when cryptographers or security people say, I protect against a global passive adversary, that means that any information that comes out of that link that could be used by the adversary cannot harm the security of your system. Okay? And that's cool. That's a really nice thing to have in a system. Now, when a system says, I protect against a partial adversary, okay, namely that can observe only some links but not others, what that means is, it's not just the case that it says, if the adversary can see everything about the other links, I lose. It means that if the adversary can see anything at all, directly or indirectly about those links, you lose. So it makes an extremely strong assumption. It is not just an assumption that the adversary cannot just physically sit on that link, or cannot just get like NetFlow or TCP dump from that link. It means that any information flow from the links that you're not able to observe to the adversary potentially would harm your system. Okay? So it really defies the laws of nature to say my system is secure only if the adversary cannot see something, because as we know from forensics, any physical action has some kind of impact, direct or indirect, into the world. This insight was the insight that allowed us to do indirect traffic analysis attacks against Tor within its threat model back in 2005. Okay? Actually, first I will show you the setup of the attack before you actually see this. So, as I said, the global passive adversary is an abstraction, and what if we could estimate something about the links that an adversary should not be able to observe in order to attack Tor? How do we do that? Imagine the following scenario. We have a Tor client that is our victim, that is our target. And the Tor client, as Tor supposes, opens a circuit across 3 relays and looks at a web page at a destination that is held by an adversary. It's a corrupt server that works with the adversary. Now that server would like to trace as much as possible who that victim is, who that client is, and it is being impeded into doing that by Tor. Okay? So what can they do? We assume that the adversary cannot observe the infrastructure of those Tor relays, either the relays themselves, the network connections, or whatnot. Cannot do BGP attacks, whatever. Okay? So here is what we can do instead. The corrupt server will send a regular pattern of traffic back to the victim. Okay? An on-off regular pattern of traffic. Quite, you know, quite a lot of bandwidth, but why not, right? And then what will we do? For each of the relays in the network, and we performed that attack luckily when the relays were about 40 rather than 7,000, right? But the concept is similar, even though, of course, it has to be scaled up. So for each of the relays, we will have a corrupt Tor node, that is our node, that is not on the path, though. We're not actually having a Tor node in the path, that just creates a loop of Tor traffic to each relay in the network, let's say relay number 2, and back to itself, and sends regular cells and times how long each cell takes to come back. Okay? So far, so good. I'm allowed to do that. All of that is totally within the Tor threat model. There is nothing here. In fact, it's weaker than the Tor threat model. I'm control one side, but no relays, no nothing like that. Okay, cool. So then what do we observe? What we observe is the following. If the pattern that the corrupt server has injected is this dark blue pattern here, okay? Actually, it's the light blue, the dark blue pattern is actually what is being received by the client here. The loop of traffic that I put through a Tor server that actually is relaying that connection is highly correlated in terms of its latency. So when basically my pattern of traffic is not injected, the latency is under a certain threshold. And then when my loop traffic that does the measurement of the latency coincides with the server putting load on that connection, my latency shoots up. Okay? And of course, if I keep doing that, I can detect that correlation and find out what? Find out that that Tor node, and then that Tor node, and then that Tor node are in fact the ones relaying that connection. Something that, in theory, Tor should prevent me from doing. Okay? So this is a warning against anyone who's tempted to flip around these assumptions. I mean, when we make a cryptographic assumption and we say global passive adversary, we do this not because we actually believe that there is a global passive adversary. Yes?
It seems like this attack allows you to identify the relays along the path.
Yes.
But
not the initial.
You didn't say how you identify the order or the order.
So the order is actually okay. The initial client is someone that we don't identify.
Yeah, of course.
Yeah.
You could identify, I guess, the order maybe by the small delta.
Yeah, the delay basically between the traffic coming and going is
so
what gives it to you.
Yeah. Right? And what you're really interested in is probably only the last one.
What we really care about was the first hop, because that's the hop you go and you basically break the door off.
The further from you,
yeah.
Because you are doing that.
Yeah.
Right? So you really care about that one because that's the one you need to coerce, force to do.
Yeah. So, word of warning. So when we basically have a cryptographic assumption that says, I am secure against a global passive adversary, we don't have that cryptographic assumption because we actually believe that there is a global passive adversary. I mean, that would be crazy. Of course there does not exist a global passive adversary. We make that assumption because it is impossible to tell what kind of partial adversaries there are, what kind of partial information people can directly or indirectly extract from links, and what effect those could have on our system. And therefore we say, if we're secure against a global passive adversary, we're secure from any subset of nodes being corrupt and network links being corrupt and any kind of information being extractable from the network. Okay, that's what it buys us. Now, scaling that down to a partial adversary does not do what security engineers think it does by actually saying, oh, the adversary can see those links, but not those links, because it means that really there should be no information flow between the links that the adversary cannot see and the adversary, something that is very difficult if you allow your adversary to use your system through effectively covert channels, right, and side channels. Okay, so that is an interesting observation, attack within the Tor threat model. But then there is an even more devastating attack that the gentleman who was sitting here sadly is going to miss because he asked about it. And the attack goes as follows. The idea is Tor is meant to, okay, so even if Tor is not secure against anything near the global adversary, indirect load monitoring, okay, fine. Can it at least, please, protect me against just my ISP, my internet service provider? Could it just protect me against the guy next to me with a Wi-Fi sniffer at Starbucks, right? I mean, it's not much to ask, right? I mean, it could just do that because that's totally within its threat model. The guy's a total loser. It's not like, it doesn't take an intelligence agency to do any of that stuff, right? Okay. And the answer is, well, kind of not. And here is the attack. And these families of attacks are called fingerprinting attacks. The insight behind fingerprinting attacks is that Tor does not disrupt enough the pattern of traffic on the initial link next to the client to hide enough even about the content of the encrypted communications to avoid re-identification. So when you open a Tor circuit to a website, it is not the case that you just send one message of one fixed length. What you do is you send a stream of TCP packets effectively that are packaged one by one into cells of Tor, okay? Now, that has a particular timing and volume characteristic over time, okay? And of course, the response you get back from the website, depending on which website you're actually visiting, could again have a time versus volume characteristic that is extremely characteristic of the website. Some websites have a very simple HTML page. Some websites are very heavy on images. Some websites, as soon as you go to a page, there is a video playing. Some websites have JavaScript or whatnot, or keep connections open and keep sending regular updates to update parts of the tickers, the news, whatever. But basically, the traffic that you see, even through a Tor initial client to first hop connection, is quite different across different websites. And what we can do, and what we have done, is we use machine learning techniques to visit websites through Tor, learn the stable fingerprints of those websites in terms of the traffic over time characteristics of those websites, and then look at a Tor connection of a single request and ask the question, which particular website does these connections seem to actually be looking like? What fingerprint is it close to? Okay? And our attacks work well. Let me actually say a couple more words about the setting. Now, it isn't likely, and the web is vast. Okay? It has websites, it has millions of websites, it has probably thousands of websites every day that get born and die. An adversary doesn't care about most of them. So the setting of those attacks is that the adversary has a set of target websites that they want to detect whether a user is going to. Think about what your favorite pet hate is, from illicit material to drugs to terrorism to whatever, and imagine you're an adversary that may care about, let's say, one of them. Okay? So you find 100 target websites and you do wonder, is a Tor user going to one of those websites? Now, at the same time, this is not a closed world classification problem because most people will not be going to those websites. Okay? In fact, that's key, right? So what you have to do is not only learn a good model of those websites, but learn a good approximate model of the other stuff. right? That you don't actually care so much about classifying. You just want to say, I have this other category which is the other stuff, okay? And therefore you also troll the web and make a good model of the other stuff. And then you get a connection through Tor. And then what you need to do is classify it first as, is that one of the 100 websites that I care about, or is it the other stuff? And if it is one of those websites that I care about, which one is it most likely to be? Okay, so that's the setting in which these attacks are traditionally evaluated.
So how stable is this pattern for these websites, assuming that they have like a really dynamic nature?
It is not very stable. And this is why it's very important to actually have this close set versus, oh, I have to learn the whole web. Because otherwise, by the time you've learned half of the web, the half you have learned is already old, and the other one you haven't yet trolled, right? Yeah. Yeah, absolutely. So actually we did experiments because, you know, we were asked, the paper that we wrote about this was rejected, as they do, and then had to be resubmitted. And then we were asked, oh, could you do this additional experiment that required actually collecting more data? And actually that was very tricky, right? Because we had collected the data before. The data that we were asked to collect would have to somehow be merged with the old data. And we realized that, well, actually, you know, the two are not comparable anymore. We'll have to really be fair, recollect the stuff, including the new stuff, and do it. So we actually performed that, and indeed they're not that stable over time. Yeah.
I would imagine many of these small, weird websites are actually very similar because they're probably hosted.
We will
in
see
either
actually the
Djibouti
features,
or
yeah.
Joomla or the
We will see the features that make things more distinguishable than the other ones, and you will indeed notice that size of the website is a major one.
Can you tell between two forums hosted in Djibouti? Can you say if it's a jihadist or?
No, I mean, we will look at the feature list and we will go through to exactly illustrate your point. Small websites are much more difficult to distinguish between each other than the ones with a lot of media, JavaScript, resources, third-party libraries, etc. Yeah. Okay, cool. So now, interestingly, when we apply this attack, we get good accuracy. Okay, you know, by some definition. Now remember, this is just one request, etc. We get good accuracy, much higher than the baseline. The baseline here should really have been 0.01, and we get 0.91, whatever. It doesn't really matter to me exactly what it is. Like, people are bickering all the time. Well, what about the, you know, heavy priors towards going to others, you know, base rate fallacy, etc. What really matters is, if every day you wake up and you go to a website, eventually, by repeating that attack, we will get you, right? I mean, whether it's going to be on the first request, or whether it's going to be on 10 requests, or whether it's going to be in a month, there is leakage. It is massive in comparison to the baseline. And if you basically have a normal pattern of usage through an anonymity system of actually going to your favorite websites, and your favorite websites are the ones under monitoring, we will get you eventually, right? The exact rate at which this happens is important. The important thing, though, for this particular audience here is it leaks. It leaks a lot. Now, what is, though, important is because many people earlier said, okay, cool, so Tor clearly made a bit of a daft choice by not delaying and not putting any cover. What if we do put delays and covers, right? So there were a number of padding and delaying schemes that were proposed in order to strengthen Tor against all sorts of traffic analysis, end-to-end correlation, and web fingerprinting. Okay? Morphing basically takes pages and starts trying to make them like other pages. Decode pages, load another page while you load the page you want, trying to confuse things on the assumption that this interleaving confuses the adversary. Adaptive padding basically take streams from different pages and try to make them as close as possible within some delay characteristics. Buffalo basically creates on-off periods on when basically you are transmitting or not transmitting, hoping that this hides the internal, when there is a busy period, characteristics, etc. The morality is the following. None of them reach anywhere close to the baseline. Okay? It's not the case that somehow they solve the problem. Some of them work better than others, but all of them come at a considerable bandwidth overhead, and then except a few that are both expensive and not very effective, basically what you expect is happening. The more you spend in terms of bandwidth, the better the protection you have. The protection you have never really goes to zero. In fact, it's very far off from zero. Eventually, you will leak that information within the threat model of Tor, right? I mean, that's the killer here, within that threat model. Just your ISP or just the guy next to you on the Starbucks observing your connection. Now, they will have to follow you.
Say 0.1, what does this actually...
Okay, so basically the experiment we did was we had 100 websites, okay, and we had to categorize others or this one. So what we should be expecting actually to have is an accuracy about 0. Something, right? And in fact, we get 0.91. So we're basically orders of magnitude off in doing better than the baseline. Yeah.
Are there some websites which are just bad? That's why you are going to see.
Are some websites that are bad?
In terms of that, they will, no matter how good, whatever bandwidth you are, or at least the twice or thrice bandwidth you are, they still be recognizable.
Well, okay, since this is the second question, right? What allows us to recognize websites, right? Because we actually did an analysis. So our technique, in comparison with the others that were compared in that slide, I mean, they're all comparable. It's not like, there is a bit of a race about whose is better, but now we're talking about 0.01 accuracy increases. It's not huge. But we use techniques based on random decision forest, and the nice thing about those is that they allow us to extract which features really were the most significant in being able to do the fingerprinting of the websites. And basically, the number of incoming packets, namely the packets from the server to the client for one request, was by far the most informative feature. And then basically we had number of outgoing packets as a fraction of the total number of packets, or the fraction basically of the request versus the reply, number of incoming packets as a fraction of the total number of packets, standard deviation of the packets, number of outgoing packets. So most of the features, as you can see, are global volume features, okay? And then a little bit below that, once we actually start hitting those, we actually start having concentration features, namely, what was the volume towards the beginning versus towards the middle versus towards the end of the connection, a little bit more about the shape, if you want, of the connection. But you already gain a lot of information just basically by looking at overall what are the volumes, what are the ratio volumes on the two channels in and out, etc.
How robust is the client-side caching?
It depends. The problem with client-side caching, since we have time, actually I can tell you more details than you ever wanted to have. So, when you build a Tor browser, you have this awful choice, right? On one side, of course, you don't want to hit the network very often because this, right? On the other side, you want to make sure you don't have any side channels within your browser. Okay, so the problem with client-side caching is it might solve this problem. In fact, we disable the caches to do this, of course, because we actually want to see given a request. If there is no request, then you have a problem, right? But then the problem is that this opens a covert channel and a side channel within the browser. Namely, you can do all the tricks where you request basically a page as a link or as an image from your page that someone is browsing, and depending on the timing with which it was basically fetched, you can tell if it was in the cache or not, and then do this attack on the client. So that's the problem with the caching solution. It actually creates a covert channel, a side channel effectively within the browser that then allows other attacks to happen.
But that if you control the server, right?
Yes. So for example, you browse through Tor to my server. I can tell because you come out of an exit relay. And now I wonder where you're going to one of these 100 sites. So basically what I have done is I have taken a bunch of images from those, and now I basically inject them in 1 pixel side things, and then I measure what timing you take to load them, and that basically gives me information of whether you have been there or not, right? So it's hard choices. I mean, what I'm trying to say here is not, of course, we disable caches here, but every action has a reaction. It's not, nothing is for free, yeah?
You were fairly highly precise. How accurate?
So the measures were the accuracy before. Is that?
In the sense of precision and accuracy. Yeah.
Oh, I see. So we basically measuring as a success only when we got the page exactly right. So it's not the case that we actually saw, oh, what if it is in the top 3, what if it is in the top 5, etc., right? So we don't actually have that measure. We really went for, I got exactly that page, not the same domain, not the same site, exactly the URL, right? And now, there are limitations to a study, and this is an invitation for you to improve it. For example, what we didn't do is we didn't take many pages from the same domain that may actually be confused with each other because the Chrome of the page is the same, right? If you go to a newspaper, maybe every article looks a little bit the same because the text is mostly different. Everything else might be the same content management system. So that's actually quite interesting to do, to see if there is a difference there. But then again, what is really interesting is that the task would have to be modified somehow because potentially the adversary doesn't really care about which exact page you went to. They just care that you went to this dodgy news provider or dodgy website, right? So the task becomes both harder and potentially easier, and you have to basically define your category like that. And another thing that we haven't done is to say, how independent is each request that allows us to accumulate effectively the evidence? Because, of course, we know that we will be doing better under multiple requests, but we don't know the rate. If it is truly independent samples and then we learn very fast, or if it is correlated errors or whatever that may lead us astray. Great opportunities there for research. Okay, great. So this is really an attack on Tor that Tor is very concerned about. This is why there are all these proposals that I showed you to try to fix it, and it's not really clear it has a fix that is simple. And let me give you an insight for why. So I told you already, Tor suffers from the fact that it doesn't delay. Okay, what if it did delay? Tor suffers from the fact it doesn't have cover traffic. Oh, well, okay, what if it had some cover traffic? Ultimately, Tor suffers from the fact that all messages take the same path. Right? And then when you basically see messages anywhere in the network, they basically are following the same path, etc. And that in itself makes it very inflexible to provide protection strategies and to also fix the latency and the volume and all that stuff. Okay? That's also an additional fundamental issue that you should not forget. Mixed systems, each message takes a different path. And that creates much more flexibility and ability to do things. Same path limits your options as a designer. Okay, so what other problems does Tor have to finish off on the Tor thing? Sampling attacks. Stephen Murdoch and others have shown that actually you don't have to observe the link. You can just get samples of traffic volumes, net flows, whatever, basically, and you can still do traffic analysis attacks. If you can just basically control some ASs or some internet exchanges, you can approximate global passive pretty well and actually do much better than if you just controlled a router, obviously. BGP rerouting attacks will give you the leverage that maybe the global adversary would have. And of course, you have a lot of the epistemic denial of service attacks that we also looked at the mixes applying to onion routing systems as well. Except that onion routing systems are more fragile than this, so no one really cares about deploying those attacks. Okay, so to some extent, my conclusion about Tor is awesome. It is both too strong and too weak, right? It is too strong in some senses in terms of its cryptography, even though it's not actually as strong as mixed networks, because really, there is no point in having bitwise unlinkability between 2 points in the stream if just doing trivial traffic analysis might actually give you linkability already. I mean, it's not a bit pattern that will betray you, it's the actual timing that will betray you pretty fast. So, is it really necessary to do a lot of heavy crypto? Couldn't you just relay the packet, do something simple end-to-end and be done with it, right? So it's very strong in that sense, too strong in that sense. But of course it is too weak in other senses. And we have done some modeling, we tried to formally show things about Tor, and really it comes down to the fact that it is as strong eventually under multiple observations as single hop relays. I mean, because of all of these attacks, if the server is bad, okay, basically what gives you your security is your stable guard. This one node or 3 nodes that you always connect to the Tor network through. If that is bad, you're dead. And you know, frankly speaking, that is a single hop relay in terms of traffic analysis resistance against a destination that is malicious. It's not actually that different quantitatively than a single hop relay, which is a very harsh statement to make to some extent, right? That there is all this engineering, we poo-pooed a little bit the single hop relays at the beginning saying we don't like them, but actually Tor could be modeled as a collection of single hop relays. Okay, eventually, under multiple observations. So it's not so great against powerful adversaries, and then the question I get usually at this point of the talk is, okay, so you tell me Tor is a weak system, so does that mean that the big signals intelligence agencies in this world can break it? Right? I mean, that's a perfectly valid scientific question. But for it to be a scientific question, we cannot just sit here and speculate. We have to discuss it on the basis of what kind of evidence do we have to support or not support that statement, right? Namely, can the NSA, GCHQ, let's say, break Tor? Right? So what kind of evidence do we have either side? So there is some mixed evidence from the Snowden cache of documents to start with, right? So we know that GCHQ back in 2011 had a working group effectively. It was a bit of a lunch group of people who were like getting together around the question of what to do with Tor. They produced this wonderful deck of slides called Tor Stinks, okay, describing, you know, what Tor is and what kind of problems they have day to day when they try to deal with Tor traffic. So we know there was interest there. We also know that there is a set of tools, the so-called egotistical giraffe and egotistical goat, that are basically exploits crafted to be delivered against the Tor browser bundle. So this was an attack against Tor based on a vulnerability vector on its browser rather than traffic analysis or anything that I'm interested in here. Obviously, you know, that's an attack. If you can break into the client of someone who browses through Tor to you, you're kind of home, you can read its IP address, whatever. So we know that there was interest in there. Then we have the xkeyscore rules. The xkeyscore system is basically the kind of deep packet inspection, a map reduce kind of set of rules that the NSA is using to do its processing in its clusters. And we have rules for that were published helpfully a few years back by journalists who I'm not really sure knew exactly what they were publishing. And what it shows is that there are specific rules that troll through emails to extract Tor bridges, okay? So Tor bridges are distributed through email to select individuals, and we actually have the firewall rules and, the MapReduce job that picks these bridges to make a list of them. Why would you make a list of bridges? I mean, that's quite interesting, right? Anyway, so that's what that rule is there for, and also for tracking Tor downloads. Who downloaded Tor, and actually who downloaded also a bunch of other website anonymizers. Okay, so we have those rules. We know that they exist. And finally, we know that GCHQ had an internal paper that showed a technique for doing stream tracing a little bit like the template stream that I showed you. In fact, their technique was quite interesting. I wish I had known about it many years ago so that I reference it. They didn't reference my paper, which I feel a bit weird about. I mean, you know, we did a lot of work for them, but it seemed they didn't care. But anyway, so they had a paper that had a competing technique in there for how to do stream tracing, which was ideas that were reasonable. I mean, they were not very informed by the literature, but they were competitive with the literature, and clearly if you had a lot of data and you tested them, you would be able to refine them. Now, this is all we know about what GCHQ has done largely and the xkeyscore rule for the NSA. We actually don't have a smoking gun, like a slide set that says, oh, don't worry, Tor is broken, we have broken it through traffic analysis, we basically do stream correlation every day, not a problem. Not a problem. We don't have that. That's not what we have. We have those, you know, that set of evidence. Then another thing we have is the FBI is suspiciously successful in being able to unravel operations ran on hidden services. Now, suspiciously successful is explained by them through two things. First thing is they say operators make operational mistakes all the time. Super plausible. Super plausible. I mean, people make operational mistakes all the time. I wouldn't be surprised if that is the case. And the second thing is that we know they have worked, and this is not on my slide, with researchers at CMU to leverage some attacks that were known against Tor that allow you to infer more about hidden services than you should. So there is a little bit there of traffic analysis. The problem with the answer, it was all operational security failures, is the fact that this would be the answer even if it was the result of signals intelligence. Even if attacking Tor was the result of signals intelligence, you never, that's the doctrine of the UK-US signals intelligence establishment, you never basically reveal that it is a success of signals intelligence. You always must find another way of actually ascribing the success. And they would say the same if they were routinely using Tor, using traffic analysis and passing information to the FBI through their police liaison. So it's a non-informative statement to say, you know, but it's explained through whichever way, right? And again, so the conclusion there is, again, we have no information. I mean, the information we have from the FBI about how they managed to break a lot of Tor hidden services is non-informative doctrinally. We cannot actually rely on it as evidence. And therefore, the only thing we can say again is we don't know, right? However, what we do know is, given that set of evidence, what we don't know is, are they breaking Tor routinely and operationally every day? That we don't know. What we do know, however, is that at the time of the writing of these documents, 2011, all the scientific questions through this paper, the rules, etc., all the kind of operational issues, namely the collection of traffic, the rules, etc., were partially or could have been put in place, right? The access points, through other slides that I'm not discussing here, were there to actually access many bearers of 10 gigabit a second across the world, etc. And therefore, if the NSA or GCHQ are not breaking Tor at this point, is really down to a matter of policy. It's not really a matter of lack of capacity to at least have some ends of the connections. It's really maybe they have better things to do in life. I mean, that's fine. I'm not saying that they're doing or they're not doing, but the capability to do it definitely, the evidence says, was already mature enough that if there was a policy decision to say, let's do it, all my evidence suggests that they would be able to do it. Now, every time I say this though, however, I say the following. Tor, despite that statement, is still one of the better solutions out there for protecting your privacy. Don't go and start communicating in plain text because of this statement, right? I mean, of course, if you communicate in plain text, you're definitely dead. There is no, there's no need to attack you. So very often those kind of statements are misconstrued to say, go and use some other snake oil software. Don't do that. Tor is still the thing that gives you the most protection. However, it falls very short of providing you the protection you want. Which leads us, for the next half hour, I'm sorry for you, 3 hours is a bit heavy, huh? I mean, okay, I can talk about this all week, huh? I mean, to me, it's like great. In fact, if the next speaker would like, okay. All right. So the question then is, what next after Tor, right? So I have presented you mixed networks. I have presented you that they're not perfect. I have presented you Tor. I have, I hope, convinced you that even within its threat model, it falls short. Okay, I have still told you, well, Tor is still the best game in town. Don't, go communicating in plain or using some kind of weird thing that your cousin made, all right? But, I mean, it's unsatisfactory, right? It's highly unsatisfactory. We're at the stage cryptography was in the early 70s saying, well, you're better off using it, but, of course, attacks will work against it, right? I mean, don't use too much of it. Don't repeat your message. Change your keys every day. I mean, this operationally cannot really be a mass product. So what do we do about this situation? And this is the insights that I would like to give you for the next half hour. So, as I said, all anonymity systems, Tor, mixed networks, dynamic cryptographers, whatever, leak. So now we have to shift as a community towards saying this design is better than that design, absolutely, or because of threat model, into a much more nuanced approach, where actually we say we have to measure those leakages, we have to understand them, we have to understand how they compose, and we have to understand how they compose with the higher level problems we're trying to solve through anonymity, being elections, messaging, access to private information, etc. And then we have to start making quantitative assessments of, what is good enough, what are the rates of leakages, and how to actually plug them. Okay? We cannot just say, here is a padding scheme. Clearly, Tor was broken because of lack of padding. Now that I have padding, it's perfect. That's not how the world works. Okay? So we have to define metrics for anonymity and anonymity degradation. These have to rely on probability theory, of course. And we have used some entropy metrics back in 2002. But these are very far outdated. And I'll present you better ones. Now, the problem is, as soon as you start having probabilistic-based metrics for a security system, this is true for crypto, this is true for security, this is true for anonymity systems as well. I mean, that's quite a commitment, because then the question becomes, well, how do I compute those probabilities, right? How do I compute those probabilities? I mean, we're talking about very complex systems, very difficult to model, very difficult to have analytical results. Adversary observations are these dumps of TCP traffic, right? They're not mathematically beautiful objects in any way. How do I actually do that? And it took us 7 years to answer that question, even for simple mixed systems, by doing effectively Monte Carlo given a trace, working out what are the probabilities of Alice talking to Bob. We didn't run Monte Carlo simulations for 7 years. The theory took us 7 years to actually flesh out that this is how we should do it, thankfully. Okay. But however, our ability to build robust mixed networks depends on correctly measuring their leakage. And that is true also about systems that are built on top of mixed networks, because since there is leakage at the mixed network level, you have to actually include in the leakage in the high-level system. Now, my favorite anonymity notion is actually due to Aniket here, amongst other people, who proposed ANOA. And ANOA is nice because it takes some features of differential privacy and throws away other features of differential privacy, and I like that too. And it basically provides quite a natural setting that is also familiar to cryptographers, but is not too far away from what traditional traffic analysts would do with probability theory and statistical modeling to provide a definition for anonymity. And basically, and you know, I apologize, I'm adapting your ideas. I'm not actually just presenting them as they are. Even the terms are different, in fact, and I don't care. You know, that's cool. Okay, so the idea behind those kind of ANOA type definitions, I'm not even going to claim that they're exactly the ANOA definitions, is that you basically define some observations of the adversary from the anonymity system. And then you say that, you know, the adversary has asked the participants in the anonymity system to do one of two actions. In the first one, for example, Alice is talking to Charlie and Bob is talking to Debbie. In the second one, Alice will have been talking to Debbie and Bob will have been talking to Charlie, the other way around. So the adversary basically says, system, pick one of these two options. The system picks one of these two options. The system runs. An observation is generated. Now, given that observation, which is the same, you try to guess which of these two scenarios happened. Okay, by counting packets, by seeing inside what leaks from the network, etc. And the idea is that a perfect relationship anonymity, at least, system should not allow you to guess between that scenario and that scenario with probability better than half or whatever your prior was. Okay, it should leak no additional information than what you knew before. Okay? And that can be expressed in a kind of differential privacy style way by saying that for any observation here, you pick the worst observation, of course. The probability of the observation, given that it was scenario 0, is basically smaller or equal than e to the epsilon. So that's just a small multiplicative factor where epsilon tells you how big that factor is from the other probability that it was generated from here, plus delta, which is a probability that something catastrophic happened. And you know, the whole system just gave you the answer, okay, without hiding anything. So delta should be small. Epsilon is a measure of the change in your likelihood given new information, the change of the likelihood ratio, in effect. In the special case where there is no delta, we'll just use that likelihood ratio here in a future slide to indicate, you know, what is the bound on e to the epsilon, and also just that quantity as well here. Okay, so that's some notation. Now, why are these definitions nice? And why is generally, I mean, what is the trick of differential privacy? Has anyone worked on differential privacy here before I say anything rude? Oh, great. Okay, so I can only be rude to you. I'm sorry about that. The nice thing about differential privacy is basically it relates to something that people working on decision theory have used since year dot, which is the likelihood ratio. At the end of the day, if you have a decision problem, did X happen or the other happen, we always knew that the most important quantity there is the likelihood ratio. Given my evidence, what is the probability of my evidence given that, one thing would have happened or the other thing would have happened? You provide a bound on that likelihood ratio. The nice thing is that these likelihood ratios under new evidence compose nicely. And therefore, if you have an epsilon delta ANOA relationship anonymous system, then if you basically observe multiple rounds of that system, there are composition theorems, general composition theorems, that allow you to say my resulting system is the sum of the epsilons relationship anonymous and the sum of the deltas relationship anonymous. Okay, and that's nice, and people like that, okay? As I said, epsilon is a measure of how much the likelihood ratio changes, and delta is the probability of a catastrophic event, basically. So delta better be small. So it composes, we love it, but it composes terribly, terribly. Okay, and we will revisit that in a second. If you rely on the composition bounds to actually parameterize a real system, you're crazy. And we will see that in just 1 second. So this composition being really poor really opens up a philosophical question, which sadly I will only be able to really engage in a discussion with you, since you have used differential privacy before, but the rest of you can actually watch us. Which is the following. Should we be using the worst case epsilon to parameterize anonymity systems, or should we be using the average case epsilon? Now, those of you who have worked on crypto at this point should be like, what did he say? What did he say? It's a security system. We must take the worst possible observation, and we must parameterize our security, the security of the system on the basis of that. Because what if it happens? What if the worst thing happens? It's not a parameter what observation we get. Maybe I will get the worst observation, and the adversary will learn a lot of information. Clearly, we must take the worst case. Now, I am not anymore so sure about that. I started that way, and then I started measuring these things, and I'm now uncertain. And this is why, and here is my defense of actually taking average epsilon metrics. So I've already given you the argument for taking the worst case, right? I mean, what matters is what is the worst observation from the point of view of the loss of the leakage of information. Okay. Now, however, imagine we have an adversary that observes an anonymity system and gets 4 concrete observations for a correlated event. Like the adversary knows that Alice is going to send, let's say, to someone, the same person 4 times. They look at the observation, and then they get a likelihood ratio for the first one that is e to the minus 0.2. Note here that it is actually the opposite from what actually happened, right? I mean, they believe that in something false, probabilities are like that. Sometimes the most likely event is actually the other way around than what you expect. Then basically it says the likelihood ratio for the second one is e to the 0.1, again e to the 0.1, e to the 0.1 for the 3 other observations. Now, what is the total change in the likelihood ratio for defining now the observation as the composition of those 4 observations, for these concrete observations, right? Not for any observation, these concrete observations. It is what you expect e to the 0.1. How do I derive that? I just take these basically and add them, because basically these are multiplicatively composed. So that's e to the 0.1. However, imagine that system that I used had a worst case observation. A worst case observation in the system could have occurred. It hasn't occurred in this particular case. It could have occurred though, which would have led to a maximum epsilon of 1. Which is much bigger than 0.1. That's worse for privacy. My composition bound would have told me, I mean, I would have been told 2 things. First of all, that each of these observations have a loss of 1 instead of 0.1 or minus 0.2, etc. And my composition bound would have told me that since here we have 4 observations, I have a kind of loss. I have an epsilon of 4 times 1, which is 4, which is like gigantic in comparison with what I actually observed. Okay, but so far I haven't really given any strong arguments about why we should be using this average. I mean, what if this catastrophic thing had occurred, right? Then I would have maybe lost big time. However, and this is the insight here, if you observe how this quantity behaves, it basically takes a random sample from the actual random loss given the coin flips of the mechanism that create some randomness about the observation. And that quantity here, as basically I keep adding more observations, tends towards the mean of the observation times the number of observations. That's where it tends. I mean, eventually the central limit theorems and all of that will tell us that it will tend to the mean. And the adversary will not be able to beat that by adding more observations. In fact, the more observations you add, the more you will tend towards the mean. The other one, though, tends to, of course, towards a bound over the mean. Yes?
So, but then maybe I'm not expert on differential privacy, but I'll not take the O0 observation. I'll just ignore that and consider the other ones and work.
But that would make you make mistakes. That would basically say that I only pick the ones that I have a prejudice about. At that point, you have no idea which one is the right one and the wrong one. You have picked one to be above and one to be below. One scenario to be above, one to be below. You don't know that you have picked the right one to be above and below. In fact, the O0.2 is the strongest evidence in a single round you got that actually it's the one below that is the correct one. It's a bit like saying, look, there is something in the box as red or blue, right? I think that it's red, so, any evidence that gives the higher probability of being red, I will take it. Any evidence that says, oh, maybe actually it's blue with higher probability, I throw it away.
That's what we do.
I mean, that's what we do indeed, but you see what I mean, right? Both of them are valid evidence, it's not wrong. And you have to actually take them all into account to get an accurate estimate of your of who did it or whatever scenario happened. Okay, so this quantity that actually is the quantity that the adversary will have to rely on to make a decision, or maybe many decisions, it tends towards the mean. This quantity here towards, of course, towards an upper bound on actually the likelihood ratio, which is traditionally what we have looked for. But the probability of hitting that upper bound just through random selections, if that upper bound is very far from the mean under multiple observations, is itself cryptographically small, right? Because we know that the probability of a random variable going very far away from its mean, even if we know very few things about this random variable, is extremely small. So actually, that kind of composition theorem is quite catastrophic if we just take it literally. And in fact, the literature on differential privacy, to be fair, has taken a much more nuanced approach towards advanced composition theorems, etc. However, my point as an engineer, because I'm not much of a theorist, you may have worked that out, is, okay, there are nice advanced composition theorems, respect to everybody who works on them, I love them. I, as an engineer, I'm really interested in calculating this mean thing here and understanding if there are particularly, destructive scenarios that lead to a catastrophic failure, my delta. What is the delta? What is the catastrophic? Why is the delta different from having a big epsilon? A big epsilon radically changes the ratio between two possibilities. They're still both possible, but it really changes the ratio between two possibilities that are still possible. The delta gives you all the information. So these are catastrophic failures, as I call them. Big epsilons are very informative scenarios for the adversary, but not catastrophic. And nothing tells you that you might not get a big epsilon now and then a big epsilon down next time, just because you have always a regression towards the mean. Okay, so there is another advantage to actually, of course, being very respectful of the people working on having advanced composition theorem, but also, being much more serious about considering what is my average leakage, what is my average epsilon rather than the worst case epsilon. Which is that actually the average epsilon is something that poor I, engineer, can calculate through Monte Carlo methods, right? It is actually very difficult through sampling to find out the extremum of distributions, because there might be a sample that might occur with probability to the minus 128 that is actually much bigger than anything else. But it is not difficult to actually, through sampling, particularly if you know that your distributions are smoother or not or whatever, to get a mean. Okay? And then, of course, because you have relied on sampling, you know that you have not explored the whole space, and potentially there are catastrophic failure scenarios, which again you can bound that since you haven't found it in 10,000 examples or 100,000 examples, what the probability is. Now, this is a bit ropey. It should make the theorist amongst you very stressed that I'm saying these things, but please take it as a challenge to also try to think more about, okay, how do I empirically calculate my losses in the context of a very complex system that is not smooth at all to do maths in? And that would be very interesting if you find a better example on how to do that. However, we have used these average metrics, dangerous as they are, because these are the only ones we can calculate so far easily for the kind of systems that we have designed. Okay, now one thing that is good news is, so measuring anonymity, be serious about it. Be serious about it, do it in a way that systematizes the field, that, that allows designs to be comparable, etc. Lesson number 1. Lesson number 2, bitwise unlinkability, don't obsess about it, we've taken care of it. Bitwise unlinkability used to be a big problem in mixed networks, decryption mixed networks in particular. Every hacker threw together some kind of public key encryption, decryption, whatever, and said, okay, now that's bitwise unlinkable. It was a terrible idea. So we spent our tender years, myself and Ian Goldberg, building mixed packet formats that are very flexible. They allow a sender to encode messages to a set of mixes and to a destination, relay arbitrary information to each of the mixes so that they can do the routing, delaying, whatever, relay back replies that are indistinguishable, etc. We did the work for you. Unless you have genuinely a different need, don't mess with the cryptography. The cryptography is kind of done. Please review our proofs, please, improve them and all that stuff. But that's not where the money is in this field. The money really is in the traffic analysis resistance rather than the cryptography. Okay? So I'll skip that section pretty quickly. So the next step that we took in order to try to improve on Tor is very much in the line I think you suggested, or maybe someone else. We really looked, what is it that makes Tor streams distinguishable from each other? At the end of the day, this is really what allows you to do tracing. You have one stream, you see it again, you can really tell it's that stream rather than all the other ones. So what is it? And what we really found is that web traffic over TCP is absolutely horrendously irregular. Horrendously irregular. Okay? There are big on-off periods. There are no two streams that exactly have the on-off periods at the same time unless you have some mental connection with someone who clicks exactly at the same times. Even then, actually, it's not the same. Okay? So those kind of patterns of traffic are genuinely very difficult to naturally make the same across all users. Okay? Naturally make the same. However, there are other classes of traffic that seem to have much more regular patterns. One of them we identified that we thought was really interesting was voice over IP. Voice over IP, if you drop all the features that do silent suppression, etc., is potentially a regular bit rate if you don't use a variable bit rate. And every, 20 milliseconds, you send a message of a few tens of bytes, etc. And in theory, all the streams should be the same size. Okay? So we asked ourselves the question, could we build an anonymity network for voice over IP? Using that kind of insight. And in fact, we had a design, we called it DRAX. What we do is we have a friend-of-friend network with whom you have some streams open, and then you connect those streams, and all the time there are things that look like a call, whether you're making a call or not, and then we have a kind of protocol that connects streams together when actually a call is to be routed either locally or remotely with someone else. And we rely on the inherent regularity of those streams, and of course a traffic regime that keeps them regular at every hop, right? Because we cannot just assume that under jitter in the network they will keep being regular to do this. However, this is a bit of a restricted application, I have to say. So then another idea we had was to say, can we just give up maybe on the idea of full anonymity against even local adversaries, but just make the life of adversaries that try to do mass surveillance miserable. Miserable. Okay? And what do I mean by that? What I mean by that is the following. What if we really take the approach that Tor took, which says, what really matters is to have a very large network with a very large number of users. And what really matters is that there is no bit string in the network at any point in the network that really tells you, okay, that connection was linking A and B. Because that's what happens right now. Anywhere you basically intercept traffic in the network, there is a header that tells you I came from A and I'm going to B. Right? Therefore, it means that anywhere where you intercept traffic, you get valuable traffic analysis and metadata information. So can we build an architecture that makes sure that at no point in the network, there is any bit string that can easily be interpretable by the adversary as I'm coming from A and I'm going to B, so that they basically have to directly or indirectly look at links. They have to record timings, patterns, etc. And they have to, and this is really what cost, do statistics and traffic analysis. Okay? With the data centers it involves and the exfiltration that it involves and all of that misery. Okay? So we actually said, let's build Hornet. Hornet basically is an architecture that embeds ideas from very lightweight mixing and very lightweight, even more lightweight than Tor, onion routing inside new internet generation routing protocols, namely Zion in particular. Zion, it's Adrian Perry's favorite project at ETH. Zion, he's calling it. So, and the idea there is to have very lightweight cryptographic formats. All paths actually follow the shortest path in the system. It's not the case that we're rerouting around the planet. We always take short paths from A to B. It's just that when you look at a link, you have no idea which of the paths that way this is going to and which of the paths that way it is actually coming from. Okay? And that provides us this extreme form of wide deployment where in theory every router could actually be endowed to provide this traffic analysis resistance, even though it's not very strong if someone looks really carefully and has a priori about where to intercept traffic or not. The upside, though, is that we get streams in a router anonymized at 93 gigabits a second, so line speed, basically. OK. Finally, we actually said, OK, it's been 10 years now or more that we've been thinking about ideas and all the limitations and self-reflection and, meditation in monasteries and all that stuff about what went wrong with mixing. It's time to design a kind of new kind of mixed system that tries to embody some of those ideas into it. So we designed Lupix, and you're lucky if you're going to use NIC Security in Vancouver this year, you will actually see the actual Lupix talk, which will be much better than this very quick overview. And in Lupix, we mixed a lot of these ideas that I already talked to you about. First of all, we're not actually trying to provide full anonymity. Full anonymity is when Alice talks to Bob, but Bob doesn't know who Alice is. We said, really, what if we consider anonymity to be just an extension of channel security? Alice and Bob know each other. They, in fact, trust each other. They want to talk to each other. They like each other. But they want to talk through a hostile network, and they do not want the network to learn either the content of their communications, traditional encryption, or who they're talking to, namely that they're talking to each other. Okay, that's a perfectly valid security property and actually very valuable one. We meet here, we would like to have a conversation later in life. We don't want the network to find out we know each other. Cool, all right? That's the property we're trying to offer. And that's much easier to offer because you assume that the people from each other have basically each other's public keys and they encrypt end-to-end, and therefore there is no hop in the network, in the anonymity system, that is happening in clear. And therefore a lot of cryptographic attacks that involves modifying a message, seeing that it comes out as goobly goo on the other side, or dropping messages and observing that that message was the one that was dropped or anything like that, goes away. All messages in the network are bitwise indistinguishable, including the ones that leave and reach all the edges. We use providers, like your email provider. You're going to have your Lupix provider to do some form of access control, Sybil detection, and all that stuff, controversial. We use UDP for transport and loss. We do very low latency mixing. So overall, in the setting we have tested it, which is in a data center, we try to keep it to under a few seconds. We try to keep it competitive with Tor. Okay, and that's end-to-end, not just every hop. And in order to compensate for this, because you may say, well, that's insane, you're not going to be mixing with much at 1 second, we inject cover traffic. We inject cover traffic aggressively and in many forms, and we will go through that. We don't use these threshold mixes because they lead to this high jitter on RTT, which we don't want to have. We instead delay independently each message using an exponential distribution. We use our cover traffic to do active N-1 detection, and we have more or less lean mathematical foundations to help somehow with our analysis, even though, as I said, at the end we have to rely on approximation sampling and mean values for leakages to make progress. So here is a picture of loopix, which hopefully will illustrate why we call it loopix. The idea of loopix is that we use loops of covered traffic as part of our covered traffic strategy. So each user who connects to the loopix network, you have an always-on connection to the loopix network, starts off by sending a bed of covered traffic through the network back to themselves. And that creates some covered traffic going out of the user and some covered traffic coming back to the user on both sides. Mixes, this mix in particular here, also make loops of traffic that basically go to other mixes, some provider, and then back again and to themselves. Okay? And they use those streams in order to actively detect if someone's blocking them, in order to deploy other types of countermeasures to foil traffic analysis and N-1 attacks. Finally, believe it or not, some useful messaging also happens beyond having loops going round and round. A user all the time sends a bed of covered traffic ending at exit providers, okay? But when they actually happen to have a real message to send, what they do is they substitute some of that covered traffic for the real message, relay to the provider of the recipient, hopefully, and finally the recipient can retrieve the message decrypted, okay? So we have many forms of covered traffic, two forms in loop, one form end to provider that gets substituted by real traffic where real traffic is available, providing some pretty cool and observability in terms of the volumes that actually are emitted by clients here. I mean, the volume of a loopix client in theory of outgoing traffic does not change, right? Because you can transmit up to a cap and then you have to basically start delaying your traffic, okay? Which is pretty nice. And that avoids a lot of the long-term statistical disclosure attacks, etc., where you could observe in every round who was in and who was out. Many questions, many answers, so little time. Such a pity that we don't have the rest of the day together. Why do we use exponential delay instead of batching? Memoryless property of exponential delay helps us actually doing our maths fine. And also it creates less relationships between how much your traffic gets delayed and how much other people's traffic gets delayed, which is quite handy for us in terms of many things. What kind of covered traffic we covered? Why do we use UDP? Many people ask us, why do you use UDP? Just TCP between everything and life is good. But since most of our traffic in some configurations, particularly when few users are there, is actually covered traffic, why would we use TCP at any point, and then basically every time the network, due to congestion presumably, drops a covered message, presumably, having the endpoints having to retransmit the cover messages? It's much better to let the messages die, many of them probably are going to be cover, and then deal with the transmissions purely of the good messages rather than retransmitting all the cover and prioritizing that over potentially the good user messages. What topology we use? We use this kind of broad cascades of many mixes at each layer that go ahead. Mathematically, they are lean. Providers I've talked about. Mixer sending cover traffic I talked about. And the interesting question is, what happens as the system grows? Okay, so baby systems, Peter Pan systems that refuse to grow up, they can use cover traffic. You know, I have 2 users, I simulate another 10 users, whatever. But what happens when my system has 1 million users? That's the real problem with covered traffic. And this is the story. Okay, the story is that covered traffic to keep latency low is absolutely and crucially necessary when you don't have many real users. Because that's when you don't have enough traffic to have low latency. When you start having 1 million users, you can actually start tuning down your covered traffic bed, because honest users, that's the crucial assumption, honest users will still create and send messages according to a traffic schedule that is not known to the adversary and can actually, under some security assumptions, substitute the real messages for the role of the covered traffic. And that's really the great challenge here. That's the big bet, effectively. That as the system scales, in fact, we don't have to scale up the covered traffic. In fact, we can scale down the covered traffic because now we have more real traffic. Okay? Therefore, and this is the absolute missed opportunity of mixed systems. they used delay, which hurt early adopters most, because you delay most when you have fewer people in the system, instead of saying, wait a second, when my system becomes successful, I will have enough traffic to not have to actually either delay or have covered traffic, so I might as well add some covered traffic now, tune it down later, and let my system scale and not give a miserable experience to my users. So there are two two parameters that fundamentally influence security in our system. One of it is the rate of cover or other messages that are not known to the adversary that go through the system. Okay, and the higher the rate, the better privacy we get. That is for sure, although I was confused about the Tor traffic analysis situation. For Loopix, that is for sure. The more messages, the higher the rate of honest or covered traffic that goes through that is not known by the adversary, or not controlled by the adversary, I should say, the better anonymity I get. And the second parameter is the higher the delay at each hop, the better anonymity I have as well. And the two have a very regular relationship against each other. This is the result of our simulations here. So the x-axis is the rate of traffic coming through the system. The different lines are different degrees of slowing down the rate of the exponential distribution effectively. The lower the rate, the higher the latency. Okay, and as you expect, it's very regular. The more traffic we have, the more a measure of anonymity increases. And of course, the more we delay, the more it increases as well. Okay, cool. Now, of course, Loopix is interesting, but it's not the end of the story. In fact, opens more questions than it closes in many ways, as it should. Fragmentation, classes of traffic, etc. I have a big message. I need to split it into many little packets and send them one by one. How do I pick those parameters? How do I pick my size? Is it better actually to waste traffic having bigger messages for every message, or is it better to actually have many smaller messages because I don't use many bytes of padding that way? No one knows. No one has done the economics. We're in the process of doing that. Reliable transmission. Should I do a forward error correction? Should I do repetition codes? Or should we actually do a more traditional control system with acknowledgements and all that stuff? No one has answered those questions. Again, we're working on that. Efficient directory authorities. Good question. How do we do that? How do we download all the routing traffic? I had a lot more slides on how to do that, but I won't talk to you about it, sadly. Okay, and then of course, since we have those parameters, what covered traffic and what delay and all these things, who sets them? How do the clients know them? How do we decide them? I mean, we have to observe how much real traffic from honest clients we have in the system. How do we collectively determine this in a way that is not manipulated by the adversary, that does a massive Sybil attack effectively against our system, pretends that it's so popular, but in fact no one real except for you is using it. Okay, so I had a whole section about how do we actually deal with authorities, including some work that we did together, but since okay. Amir will talk to you about it, basically, is the conclusion, right? I mean, invite him. Okay, private analytics abuse. But since my time is up, I would like to just say, where's next? And thank you very much, actually, for indulging me for 3 hours.